Hi everyone, so there were a lot of questions today during the review session about this problem from the practice exam going over deriving rate laws and steady state kinetics and so forth. So I thought I'd just kind of make a video so that way people who weren't able to make it can kind of see the process and how to approach these types of problems. So in this problem, what we're looking at is the formation of phosgene from chlorine gas and carbon monoxide. And so it's using a catalyst, which is catalyst M. In this case right here, right when we're looking at the individual reaction steps within that mechanism. And so it tells us, at the beginning, right, that M is not part of the rate law, so we can completely disregard it for any of the, follow-up problems in those cases. The other part that it gives us right within the problem is it says that, step one is a fast step with an equilibrium constant of K1. And what we know, right, is that K1 is the same as the reaction rate of little k1, right, which is the reaction constant for the forward reaction over the reaction of the reverse reaction, right, which is K minus 1 in this case. And so that gives you the equilibrium constant. So we have that information right there. So part A, right, the first thing it asks us is identify the species that are intermediates in this reaction. And so the definition of an intermediate is a something that shows up in the mechanism that is not part of the original reaction, right? It's not either one of the reactants or one of the products, and it gets formed and consumed within the reaction. So if we're looking at it right here, one thing we can see in step one is that we have Cl2 that ends up forming 2Cl in that case, right? And so that Cl is not part of the original reaction. In step 2 here, we can see that that Cl is being consumed. So we should know from that right there, right, that the Cls are intermediates. It's also produced in step 3, but because both step 2 and step 1 kind of consume those, we don't really have to worry about those. And they don't, again, Cl doesn't show up in the final net reaction in this case. The next step, right, is we can see in step 2, we end up forming CLCO. And then in step 3, we end up consuming that. So that then tells us that CLCO is also an intermediate, right? So the two intermediates are going to be Cl and ClCO, right? Those are the intermediates that we have. Now that's really, really important because when it comes time to looking at deriving the rate law, we want to make sure that we remove all intermediates from the final rate law, right? Because you can't measure the concentration of the intermediates, right? Because they should be getting consumed and used up during the reaction, right? And they shouldn't be, remain at the end. So that's an important part. Now, the next thing to think about, right, for part B now, we're deriving the rate law for the overall reaction. So the approach that we're going to want to do, because we are forming intermediates, is we're going to want to use the steady state approximation. So the best use of the steady state approximation is going to be for an intermediate that is produced in only one step and then also consumed in only one step, because then that allows us to very easily relate those reactions to each other and then start deriving everything from there. So looking at this right here, let me just erase all that stuff that I had drawn around the different steps. What we can see here, right, is that step 2 forms CLCO, step 3 uses CLCO, right? And so both of those use those up, whereas in the case of Cl, right, it's a product in step 1, it's a product in step 3, and it's consumed in step 2, but that would make it incredibly messy to deal with, I think, in my opinion, when trying to use that as our initial basis for the steady state approximation. So I would say, basing our steady state approximation on the CLCO is going to be the easiest thing to do. Now, the definition of the steady state approximation is that the rate of production, right, so that's going to be the change in concentration of CLCO, is going to be equal to, over time, right, is going to be equal to the rate of consumption, right? So negative delta CLCO over delta T, right? So we're going to have those parts right there, right? So both the rate of production and the rate of consumption should be the same, right? And so, just kind of going over reactions in general, right? When we're looking at a reaction progress for anything that we're using the steady state approximation on, there should be an initial rise, and then it should just stay the same for a while until basically everything is used up, and then it should decrease again. And so most of the time in the reaction, right, we're going to be sitting in that region where the overall concentration is completely staying the same between the rate of production and the rate of consumption of CLCO. So what we can do is we can write out all the reactions where we're forming CLCO. So we can see in step 2, right, the forward reaction is going to form the CLCO. So we know that the change in concentration of CLCO over time to form it is going to be then equal to the rate constant K2 times the concentration of Cl times the concentration of CO, right? So that's going to be that rate right there. Now the rate of consumption in this case right here, right? That's going to be equal to the following reactions, right? So I'm just going to write that out. So this is the rate of consumption, which I indicate as negative delta CLC concentration of CLCO over negative or over delta T. And so that's going to be equal to, first off, the reverse reaction, right? So because this right here, the step 2 is in equilibrium, the CLCO is also going to go in the reverse reaction to reform the Cl and the CO. So we're going to have, that's going to be K minus 2 times the concentration of CLCO. And now it also has the reaction where the CLCO is reacting with the Cl2 to form our final product of Cl2CO. So both of those reactions together are going to be contributing to the removal of the CLCO from the overall reaction mixture. So that's going to then be plus K3 times CLCO plus Cl2, or not plus Cl2, sorry, times the concentration of Cl2, right? So we have those two things right there together. And because we had said, right, we're doing the steady state approximation where the rate of consumption is going to be equal to the rate of formation, we can now set these two equal to each other. And so that's going to then be equal to K2 times Cl, concentration of Cl times the concentration of CO. So now we have this right here set up. So for the steady state approximation, what you want to do is you want to get everything essentially equal to the concentration of CLCO, so that way you can plug that back in to your overall, final rate step. So now that we have all of this right here, the next step that we want to do is for this first part, is we want to pull out the CLCO, right, because it's part of those things right there. So what we're going to do is we're going to simply pull out the concentration of CLCO, right? And so what we get then is K minus 2 plus K3 times Cl2, right? And that's going to then be equal to K2 times Cl times the concentration of CO, right? So we have this right here now. So all I did was just simply pull out the concentration of ClCO from everything here on the left side, so that way it looks all nice and neat. And so now we can just simply divide this and bring that over. So what we have now is the concentration of ClCO is going to be equal to K2 times the concentration of Cl times the concentration of CO over K minus 2 plus K3 times the concentration of Cl2, right? And so that's what we get right there in this specific case. So now that we have all of this right here set up, right, we have, essentially what the concentration of ClCO is. The next thing that we have is K2 times the concentration of Cl times the concentration of CO over K minus 2 plus K3 times the concentration of Cl2. Now, Cl is an intermediate as well, and so it's not something that's observable. And so what we want to do is we're going to want to pull that out. So now I'm just going to go to the next slide. So let me just carry over what the work I've already done here, right? So we already have established that the concentration of ClCO is going to be equal to the concentration of K2, right, times the concentration of Cl times the concentration of CO over K minus 2 plus K3 times concentration of Cl2. So we have that right there. Now, from step 1, right, one thing that we know is that, essentially we're in a fast equilibrium. And so that means that, the rate of the reaction in one direction is going to be equal to the rate of the reaction in the other direction. And so what we then get is that from step 1, right, if we look at that right there, the reaction that we have is Cl2 plus the catalyst, K1 over K minus 1, right, is going to form, oh, wrong direction, is going to form 2Cl plus M. In this case right here. Excuse me. Right, so we have this right here. And so if we write out, essentially that reaction, so the forward reaction rate is going to be simply K1 times the concentration of Cl2 is going to be equal to K minus 1 times the concentration of Cl squared in that case. And so we can rearrange this, and so that simply becomes K1 over K minus 1 times the concentration of Cl2 is equal to the concentration of Cl squared. And since we just want to have regular old Cl, we can just simply take the square root of both sides. And so if we do that, what we then get is K1 over K minus 1 times the concentration of Cl2, power of 1/2, is equal to Cl. Now, one easy thing, right, that we can think about is that K1 over K minus 1, that's the equilibrium constant, right? And so that's going to then just simply be, oh, zoomed in, right? We can rewrite that as essentially being, big K1 times the concentration of Cl2 to the power of 1/2 Cl, right? And so we can just work our way then through that and then just simply have, right, K1 to the power of 1/2 times Cl2 to the power of 1/2 is equal to Cl in that scenario. So we have that right there. Sorry. And so now what we can do is we can take this and we can plug that into here. So now what we have is that the concentration of ClCO is equal to K2 times equilibrium constant 1 to the power of 1/2 times the concentration of Cl2 to the power of 1/2 times the concentration of CO, right? Because all I did was just simply plug what we had got from step 1 for the concentration of Cl into there. And then we just divide that by K minus 2 plus K3 times the concentration of Cl2, right? So now we've made our steady state approximation that the concentration of CLCO, right, is dependent upon those factors right there. Now what we're doing is we're deriving our rate law based on the formation of our product, right? So the formation of our product is the concentration, change in concentration of Cl2CO over delta T, right? And so if we go back to our reaction, the only step where that's happening is step 3, where we're forming the Cl2CO. So that rate of reaction is K3 times the concentration of ClCO times the concentration of Cl2, right? So we have it here, right? K3 times the concentration of ClCO times the concentration of Cl2 in that case, right? So that right there is the rate. But the ClCO is an intermediate, but we've used the steady state approximation so that we can cancel that out in our rate law in this case. And so all we have to do is just simply take everything that we've approximated right there, and we plug that into here. And so if we do that, what we get as the rate then is K3 times K2 times equilibrium constant of K1 to the power of 1/2 times the concentration of Cl2 to the power of 1/2 times the concentration of CO times concentration of Cl2, right, because that comes from right here. Divide all of that by K minus 2 plus K3 to the power times the concentration of Cl2, right? So all of this right here just simply comes from right there, right? So all of that's right there. So if we simplify it a little bit more, jumped ahead a little bit more, right? We can just simply take the Cl2 to the power of 1/2 and then multiply that by Cl2 to the power of 1. And so what we should then get is that the constant, or the rate law, is K3 times K2 times equilibrium constant K1 to the power of 1/2 times the concentration of Cl2 to the power of 3/2 times the concentration of CO over K minus 2 plus K3 times the concentration of Cl2, right? And that right there is our rate law in this case, right? And so the big things really is making sure that when you're setting up your steady state approximation, that you have everything that is forming the CLCO on one side of the equation, everything that is consuming the CLCO on the opposite side, right? And then you just simply pull out the CLCO, so that way you can essentially rearrange the equation, right? Use your algebra to then figure out, what that should be, and then plug it into, the final rate law for the step 3, so that you can get the overall rate law of your reaction in that case. And then making sure things are reduced and worked out and everything. The next thing, right, part C, jumping ahead here. Right, asked, if we know the overall order of the reaction is 1.5 from experiments, which step is the rate determining step? Write the simplified overall rate expression. So if we go back, right, if something's going to be 1.5 in this case right here, then that means that you're going to have to then have as one of the steps, right, is going to be the one that has the that sets the Cl2 to the power of 1/2 in that case. And so if that's going to be the scenario, we already did it as if Cl3, right, essentially was the rate determining step, right? That was basically what part B was, right? We assume that the whole reaction, that step 3 is going to be the slowest step, so we get what the overall rate law is in that case. So if we take a moment and we look then at step 2, right, step 2 in this case, step 2 in this, come on, buddy. Step 2 in this case, right, had as its reaction rate, right, the forward one is going to be K2 times Cl times CO in that case. And so if we take the thing that we had derived from step 1, right, and we plug that into here, right, what we get then is K2 times big K1 to the power of 1/2 times the concentration of Cl2 to the power of 1/2 times the concentration of CO. And so now, right, in this case right here, if this is the reaction rate, right, you have an order of 1.5, right? And the order is only dependent upon the exponents of the concentrations. It has nothing to do with any exponents or anything related to the rate constants, right? It's only related to the exponents of the concentrations in this case. And so another way that you can write it out, right, is because these guys are constants, you can just simply say, right, K observed is equal to Cl2 1/2 times CO. But that's it, right? So that's how you derive the rate law for this specific reaction mechanism, in this case using the steady state approximation.